Hello everyone. In this video, we will go over Sudoku and an n by n grid. We will make a case for why this problem is NP-complete by showing appropriate reductions and time complexity. First of all, we need to understand what is the Sudoku problem. So Sudoku is basically a logical puzzle where you have to fill each grid from 1 till n numbers. We have a few constraints for each of these rows. For each row can only contain number from 1 till n. Similar is the case for each column and for each subgrid labeled here by red. However, each row can only contain one number once. Similar can be said for each column and for each subgrid. So you cannot have repeated numbers in any row, in any column, or any of the subgrid. Now let's look at Sudoku as sort of a decision problem. We can formulate the generalized Sudoku problem as a decision problem as follows. For example, we would have an n by n grid that would insert into an algorithm, and that algorithm would decide whether an appropriate solution for n by n grid exists or not. We will show this by building a polytime verifier and making a case for the NP completeness of this problem. So first of all, we need to show that Sudoku is a member of NP. To show that, we will build a polytime verifier. In this verifier, we will use a filled Sudoku grid as our certificate that would help us compare each row and each column and each subgrid to make sure that our solution can be verified. So first of all, we would check for each row whether each row contains a unique number and it matches our verifier. Then we'll do the same for each column, and then we'll do the same for each subgrid. This entire process will take us O to the n to the power O n cube, which is in polynomial time. Now let's try to reduce our SAT to Sudoku problem. So first of all, we would need to understand. So what KCNF basically means is each clause will contain K literals. In our example, we have 3 CNF, so each clause only contains 3 literals. And what this problem reduces down to is we have to find an assignment in such a way that our output is 1. We can see in our 3CNF example here that inputting x1 as 1, x2 as 1, x3 as 1, and x4 as 0 will generate the value 1, which is the correct assignment. Now we will try to reduce our SAT to Sudoku. Before we do that, we will make sure to define few of the rules. First of all, each clause in our SAT problem will represent a row, column, or subgrid in our Sudoku. Next, each literal in the clause will correspond to cell within a block. For example, the first literal will be labeled x11, the second will be labeled x12, and so on. We will use the naming convention of xij, where I will represent row and j will represent columns.
All right. So let's go over the encoding rules. And these are pretty similar to the rules of Sudoku, but it's basically a summary of what we need to check. So we need to check that every cell in a row has at least one number assigned to it and that it is within the range. So we are not assigning a number that is greater than n. Each row does not have any repeated cells. Similarly, we do the same for columns, and then we need to do the same for subgrid. So essentially, what we will have in the end is a collection of clauses and individual literals in between that is checking for those rules. And so the only way for the SAT formula to return a 1 is by ensuring that each the rules in each row, in each column, and each subgrid is filled. So we need to merge all these rules together and encode those literals into the Sudoku grid. And then we need a correct assignment to the SAT problem such that all those individual clauses are filled, the row constraints, the column constraints, the subgrid constraints, and then that will result in a 1. And what resulting in a 1 means that we have a valid solution for Sudoku. So next slide, please. So what this essentially will take, let's do an analysis of it by considering a very generalized Sudoku grid where we have n variables and m literals. So creating the Sudoku grid, and in this case, we have a Sudoku grid that's n by n. Setting it up will take at max O n square time, where we assign each individual variable to a specific row, column, and subgrid. And then we need to enforce the SAT clauses, so we need to check for them. And so we have m clauses and then within those clauses we have k literals. So that comes out to be O of 3mk, which is pretty much equivalent to O of m. So in the end, what we have is a time complexity of O n square plus m, which is a polynomial time complexity. Next slide. And that's important because that means that a generalized Sudoku is actually a NP complete problem. Why? Because we know for a fact that the SAT is an NP complete problem, and since we can reduce SAT to Sudoku in polynomial time, so we know that solving a Sudoku is at least as hard as solving the SAT problem. And we also know from a previous slide that we can check for a valid solution of Sudoku grid in P time. So that makes SAT Sudoku NP complete. Thank you very much.
Okay, bro.